Hi, this is Dr. Shoykot Majumdar. Under Basic Physics course of Diploma Engineering, we will discuss wave theory and interference of light. It is in submodule 4.4 of Unit 4 of light. The basic objective is to determine the intensity of superposed light waves, conditions for constructive and destructive interference, intensity of interference fringes. We will start with the Huygens principle. This is the learning objective today. Christiaan Huygens, a 17th century Dutch mathematician and physicist, is a physicist, astronomer, probabilist, horologist. In 1678, Huygens proposed that every point on the wavefront of a wave was the source of spherical wave. The resultant wave is determined by adding all the waves from the point sources. Consider a point source of sound. Step 1. Draw a spherical wave around the sound source. This is the sound source. Draw a spherical wave. Step 2. Draw a few equally spaced points, here shown in blue dots, on the circular wavefront. These are the equally spaced points on the circular wavefront. Step 3. Draw arcs of circles around each point on the wavefront. So this is the each point. Draw the arc on the circles. Draw a curve. This is the curve, the outer black circle, tangent to the individual circular wave. These are the individual circular waves. So this is the curved surface, black, colored in black. So draw a curve tangent to the individual circular wavefronts from the point sources. So these are the blue arcs. So what about plane waves? Can be created by dropping a straight streak horizontally into the pond. These are the points. The streak is like this. This is a straight streak. Drawing using Huygens principle, consider wave propagating to right from this direction to this direction. So this is the first one. This is the incident wavefront. These are the point source of disturbances. These are the circles, circular wavefronts. These are the wavefronts. These are the wavefronts. Now it is propagating. So it is this point. We are drawing a tangent here. So this is another wavefront. Now there are 1, 2, 3 wavefronts are there. So 3 wavefronts, these are the black lines, are shown on the drawing on the right. 1, 2, 3. We can continue drawing more wavefronts on the right. So direction of the propagation of wave is, this is the direction. As the wave propagates, it remains as a plane wave. Wavefronts are shown by black vertical. These are the black vertical lines. So these are the wavefronts. Now question time. Imagine the situation. You are at a show, and the show, its name is Who Wants to Be a Billionaire? and you are presented with this $1,000,000 question. What does the shape of the wavefront look like after it passed through the slit? This is a slit. These are the wavefront. When it is passed through the slit, what will be the shape of the wavefront look like? These black lines represent crest of plane wave, and this is the slit. Option A, this is the shape. Option B, this is the shape. Option C, this is the shape. At this point, anybody might panic. But if you know Huygens principle, there's nothing to be afraid of. Note that the wave propagates to the right. The wave eventually reaches a slit that is wider than its wavelength. So this is the slit. Its width is more than the wavelength of the wave. Now start drawing the waves or wavefronts using Huygens principle. The red lines represent newly drawn wavefronts. These are the circular envelopes. Now this is new wavefront, and so on. Newly drawn wavefronts. Now this circular wavefront is meeting with another circular wavefront. Then there it is meeting with another. It is meeting with another. When these are meeting at this point, there will be maxima. Again, when they are meeting in phase, another maxima. This is maximas are produced. So when this circular wavefronts meeting at this point, if you draw another envelope, this is the red line. Again, these are meeting at these points, another envelope. If we draw another envelope, so this is how the wave will propagate from left to right. So more clearly, this is what the propagation of the wave looks like as the wave passes through a slit that is wider than the wavelength of the wave. So this is the figure, or this is the picture that will be matched with the previous options. So these are the options A, B and C. So answer will be B. So our answer will be B. Now let's wrapping up. In the previous example, we have successfully used Huygens principle to show what a diffraction of wave through a slit would look like. It shows how the shape of the wave fronts is slightly curved after passing through the slit. Let us come to the slide. Here it is shown in a pond. A stone is thrown and the ripples are formed. So this is the primary source of disturbance, and the wavefront is moving from this direction to this direction. It is from center of this circle towards the right, as well as center of the circle towards the left. So there it is, the concentric rings are moving towards the end of the pond. Now Huygens principle, each wavefront is the envelope of the wavelets. These are the wavelets. So this is the envelope. Here these are the points. Here if we draw the semicircle enveloping this source of disturbances, so this is the envelope. So each point on the wavefront acts as an independent source to generate wavelets for the next wavefront. AB and CD are the two wavefronts shown here. Here, these are the crest, these are the troughs. Crest, troughs. So this is how it is propagating. Now, same picture as we have shown earlier. This is a spherical dipper. Now, shape of waves, these are concentric circles. So direction of the waves is this. So the waves are propagating along the arrow. Now what is wavefront? A source of light spreads its disturbances in all directions, in vacuum or in homogeneous medium. The points, those are situated at equal distances from the source of light, will vibrate in the same phase. Any moment, the continuous locus of all such points having the same phase of vibration is called wavefront. So this is a point source. So it is creating the secondary source of disturbances. So enveloping this one, it is a secondary wavelet. So there are many secondary wavelets. If we envelop in a hemisphere as a hemisphere, this is the secondary wavefront, and if we join the centers of the secondary wavelets, this is the primary wavefront. Okay. Now, for a spherical wavefront, this is a point source. It is propagating in all directions. That means these are the secondary source of disturbances in all directions as a sphere, spherical wavefront. In case of cylinder, just look like a cylinder, it is cylindrical wavefront. A plane wavefront, just like a cardboard, it is blocking the light of the torch. If a torch is glowed, if cardboard is placed in front of the light of the torch, then the wavefront that is produced on the cardboard is the plane wavefront. Now, interference of light. What is the definition of interference of light? When two wave trends coming from coherent sources superimpose each other, produce alternate bright and dark bands. This phenomenon of light is known as interference of light. Now the question is, what do you mean by coherent sources? Two sources of light emitting light waves of the same frequency, same or nearly same amplitude, constant phase relationship, and the sources are virtual. Now Young's experiment. Here this is the source, there is a pinhole, this is a single slit, another pinhole is there, A and B, this is a double slit. So when the lights are passing, suppose these are the crests are passing, already in our previous slide we have discussed from Huygens principle, they will superimpose and they will produce bright and dark fringes. Thus, these are the patches. If blacks are the dark and blues are the bright fringes, this is how we will get the fringe pattern. These continuous lines are representing crests and white parts are the troughs. When these continuous lines intersect each other, then they are meeting in phase, these points. So if you draw these parts, this one, this one, this one, this one, this one, and so on, it will produce a maxima. Okay, when this continuous line and white parts are meeting, they will produce minima. So this is, if blue is the bright and black is the dark, then maxima, and this part will be minima. Again it will produce maxima, then minima, and so on. This is how consecutive fringes will produce. Now the conditions for sustained interference. First point, sources must be coherent. Coherent means same wavelength, amplitude is same or nearly same, and they must maintain a constant phase relationship. Number 2, sources should be very narrow. With the increase of slit width, the coherence property will be lost. Number 3, slit separation will be very small. Otherwise, overlapping of bright and dark points will hinder interference. And finally, the separation between source and screen will be optimum. So now let us find out the expression of intensity. So these continuous straight lines are representing the incoming waves. It is coming from this direction towards this. There are two small slits separating by distance d, and a screen is placed at a distance of capital D from these two sources. Consider two interfering sinusoidal waves. X1 is represented by A1 sine of omega t, and X2 is represented by A2 sine of omega t plus delta. After superposition, these two resulting waves becomes x is equal to x1 plus x2 is equal to, by simplification, A1 plus A2 cos delta sine of omega t plus A2 sine delta cos of omega t. Here A1 is the amplitude, A1 and A2 are the amplitudes, omega is the angular velocity, and delta is the phase difference between these two waves. Now let us consider A1 plus A2 cos delta is equal to R cos theta, and A2 sine delta is equal to R sine theta. So we can write, putting these two into this equation, this one is R cos theta sine omega t, and this one is R sine theta, this one is R sine theta cos omega t. So putting this, we will get this equation x is equal to R sine of omega t plus theta, where R is the R is the amplitude, and R can be calculated as R square is equal to A square plus A1 square plus A2 square plus 2 A1 A2 cos delta. Now intensity is the square of the amplitude. Intensity is directly proportional to the square of the amplitude. So we can write I is proportional to R square. So if the constant is 1, we can write I is equal to A1 square plus A2 square plus 2 A1 A2 cos delta. If A1 is equal to A2 is equal to A, say, then we can write R square is equal to 4A square cos square delta by 2. Thus the intensity I is equal to 4A square cos square delta by 2. Already we have said A is the amplitude of the waves and delta is the phase difference. Now the conditions of constructive interference and destructive interference. Let us first start with the constructive interference. Now cos delta, its maximum value is 1, then, and the condition, if cos is equal to cos theta is equal to 0, that means delta cos delta is equal to 0, then it is 1. So it is 2n pi, cos 2n pi. So delta is equal to 2n pi, n starting from 0, 1, 2, 3, etc. And the corresponding path difference is n lambda. As we know, the relation between phase difference and path difference is phase difference is equal to 2 pi by lambda into path difference. So if it is delta is equal to 2n pi, so 2 pi by lambda into path 2 pi by lambda into path difference is equal to phase difference, or path difference is equal to phase difference into lambda by 2 pi. So this 2 pi will cancel out. So there will be n into lambda. So corresponding path difference becomes n lambda, where n is equal to 0, 1, 2, 3, etc. Now for destructive interference, the minimum value of cos delta is equal to -1. So we can write it as cos 2n plus 1 pi. Thus delta is equal to 2n plus 1 pi, where n are the natural integers 0, 1, 2, 3, etc. From the same formula, phase difference is equal to 2 pi by lambda path difference, we can find out the corresponding path difference. The corresponding path difference is 2n plus 1 lambda by 2, where n are the natural integers 0, 1, 2, 3, etc. Now ratio of maximum to minimum intensity. Now just back to the previous slide. I max will be if cos delta is equal to 1, then it becomes a1 plus a2 whole square, and I mean will be cos delta is a -1, so I mean will be a1 minus a2 whole square. So I max will be a1 plus a2 whole square, I mean will be a1 minus a2 whole square. If we come to this expression, so I max to I mean is equal to a1 plus a2 whole square by a1 minus a2 whole square. If a1 is equal to a2, then I max will be 2a whole square, that means 4a square. I mean will be 0. Now this is the intensity distribution pattern. So these are the bright fringes and the dark spots are the dark fringes. Now come to the intensity formula. I is equal to 4a square cos square delta by 2. If we write this delta is equal to phi, say, then 4a square cos square phi. So phi is equal to 0 means the intensity will be 4a square. Phi is equal to pi by 2 means I will be 0. So come to this picture. So here if we represent phi is equal to 0, then I will be 4a square is maximum, I max. Phi is equal to pi by 2 means cos phi will be 0, so the intensity will be 0. Again phi will be 3 pi by 2 means 1. Again phi will be 3 pi by 2, that means I will be maximum 4a square. 2 pi, phi 2 pi means cos delta 0, that means it is I becomes 0, and so on. So this is the intensity distribution pattern of the interference fringes. Fringe width. What is the fringe width? Separation between two consecutive dark or bright fringes is known as fringe width, and it is represented by beta is equal to lambda capital D by small d. Lambda is the wavelength of light and D be the separation between source and screen, and small d represents the separation between two slits. So this is the fringe width. This is a dark fringe, another dark fringe. So separation between these two dark fringe is the fringe width. Again, this is the dark fringe, this is the fringe width. This part is the fringe width. If we consider bright fringe, separation between two bright fringe. This is the bright fringe, this is bright fringe, middle one is the fringe width. Again, bright to bright fringe width. So this is how we can find out the fringe width. And the formula is beta is equal to lambda capital D by small. We can calculate fringe width if we know the values of wavelength of light, separation between source and screen, and the separation between two slits.